All right, welcome back from spring break. Hope we're all ready to dive into some equilibrium math. This is going to be the review for the practice equilibrium problems that we started the day before we left for break, which was 2 Fridays ago. So, I'm not going to do all the problems here. I'm going to start with one. I'm going to do one of each type. Hopefully, that will give you enough to go back and look at the others. And I may post a key as well to the remaining problems. But this will give you an idea of how to solve these different types of problems. So the first one here says write the chemical equilibrium expression for the following reaction, which is 4 moles of HCl gas reacting with 1 mole of oxygen gas in equilibrium with 2 moles of chlorine gas and 2 moles of gaseous water vapor. Okay, this is an easier one because it doesn't have any numbers to chug, so we're just going to have to write the expression. The expression always is this: the KEQ will be equal to the concentration of products divided by the concentration of reactants. So for us, we just need to focus on these chemicals here. We've got reactants on the left, products on the right. So when I write my equilibrium expression, it will go like this. The KEQ for this reaction will be equal to the Cl2 on top, and I'll put brackets to denote concentration. That's a product, he goes on top. And notice there are 2 Cl2s, so I'm going to actually put 2 of them in there. And there are also 2 waters, so I'm going to put 2 waters in there. Okay? Divided by, on bottom I have 4 hydrochloric acids. That's going to get busy. 2, 3, 4, and 1 oxygen. Like so. Now, of course, no chemist actually writes it like this. We always condense. So Cl times Cl is this, or the concentration of chloride times the concentration of chloride is the same as the concentration of chloride squared. So I can square my Cl2. I have 2 waters, 2 times the concentration of water, or sorry, water times the concentration of water, which is water squared. On bottom there are 4 HCl's, so that'll be the concentration of HCl to the 4th, and then O2 is just by himself. That is my equilibrium constant expression. The concentration of the chloride squared times the concentration of the water vapor squared divided by the concentration of the hydrochloric acid or hydrogen chloride gas to the 4th and divided by the concentration of oxygen. So this is always how you will set up your equilibrium constant expression. The products on top, the concentrations raised to the power of their molar coefficients. So if you went up here, the molar coefficient for chloride was 2, and the power of the chloride down here is also 2. All right, good stuff. We're going to use that in all the next problems. So going on to the next one. Here's our next one. This is number 3. At equilibrium, we have a concentration of hydrogen chloride equal to 0.0625 moles per liter, and the concentration of H2 is equal to the concentration of Cl2. Both of them are at 0.00450 moles per liter. And then they give us the reaction. Hydrogen gas plus chlorine gas in equilibrium with 2 hydrogen chloride gas. And this one is asking us to find KEQ. Okay, KEQ we know is products over reactants. Well, here there's only one product, and it is HCl. We'll put his concentration in brackets, but there are 2 HCl, so I'm going to square them because there's a 2 in front in the reaction equation. Then I'm going to put him over the reactants, products over reactants. So I have H2 on bottom, his concentration. He only has a coefficient of 1, so I don't have to do anything there. And the Cl2 also has a coefficient of 1, so I'm not squaring or giving a power to any of those. If I do, it's a power of 1, which doesn't change anything. So that's my KEQ. Well, for this particular KEQ, I have numbers. Here they are. I know my HCl, and I know both my H2 and Cl2 are the same here. So I will do this. I will plug those in. On top, my HCl is 0.0625 moles per liter, and I have to square that because it was HCl squared. On bottom, the H2 is 0.00450, but so is the Cl2, so that's 0.00450 on the bottom. So this is an equilibrium constant expression where I have put in the concentrations that I know for each of my chemicals. Alright, and I'm going to need my calculator for this one. So let's do this. We're going to have 0.0625 divide by 0.00450 and divide by 0.00450, and I get a big number actually. I get 192.9. I'm going to round that to 193 because I have 3 sig figs here. 193 is my KEQ. Big number. Big number. So think about this. If the concentrations in products and reactants had been completely equal, we would expect an equilibrium constant close to 1. Top and bottom would be mostly equal. This is a very big equilibrium constant. So that means the forward reaction that creates the products is much faster than the reverse reaction. So if I'm looking here, I'm losing H2 and Cl2 a lot faster than I'm losing HCl. I'm gaining HCl faster. Because the forward is going faster. And that's indicated by this big number. A number bigger than 1. Any number bigger than 1 means the forward reaction is faster than the backward reaction. Okay. Let's go on. Number 5. For the reaction, a similar reaction, only this time instead of chlorine gas, it's iodine gas. We have hydrogen gas reacting with iodine gas in equilibrium with 2 hydroiodic acids or 2 hydrogen iodides at 425 Celsius. Calculate the concentration of the HI, given that we know the concentrations of H2 and I2, and they are both 4.79 times 10 to the minus 4 moles per liter, and they give us the K, which is important. They give us K equal to 54.3. First step is always going to be the same. We got to set up our equilibrium constant expression. Okay, here's my KEQ. Should be equal to products over reactants. Product in this case is HI. So put a bracket around him. And it's squared because there's 2 of them. On bottom, I should have an H2. He has a coefficient of 1, so I don't have to give him any powers. And I have an I2, which has also got a coefficient of 1. So that's my equilibrium constant expression for this reaction. Now let's plug in some numbers. They told me that both my H2 and I2 have the same value, which is 4.79 times 10 to the minus 4. So if I do this again, whoops, get rid of that. So, on bottom, H2 is 4.79 times 10 to the minus 4. So is I2. Okay, I2 will be 4.79 times 10 to the minus 4. On top, however, I don't know my HI concentration. In fact, they're saying calculate the HI. So I'm going to leave that as it is. That's just HI squared. What they do give me, however, is a K value. So my KEQ, I can just put that in. It's 54.3. Again, a number that's much bigger than 1, so the forward reaction must be very fast. So I would expect the HI concentration to be larger than the H2 concentration or the I2 concentration, if that number is bigger than 1, which it is. Okay. Now I can solve this. So here's what I'm going to do. Let's give myself some room here. I want to get HI by itself, so I'm going to multiply on both sides of the equation by this 4.79 times 10 to the minus 4. I'm going to have to do that twice, actually, which is going to move it all to the other side. So what I'll eventually get is 4.79 times 10 to the minus 4 times 4.79 times 10 to the minus 4 times that 54.3, okay, and that will equal my concentration of HI squared. Alright, if you got this far, good stuff. I'm going to recommend this because a lot of calculators can't handle powers of 10. Just multiply those 4.79s and that 54.3 together. You can do the 10s in your head. You know 10 to the minus 4 times 10 to the minus 4 is going to be 10 to the minus 8. Okay? So let's do the other bit here, which is 4.79 times 4.79 times 54.3. And my calculator is telling me that I get 1245.86, etc. I'm not going to round this yet because it's not my final answer. Equal to HI squared. Almost done. There are a couple of, if you're good at algebra, you're going to know that the last step is going to be just square root both sides. But you may not have much experience taking square roots of powers of 10. So let me give you some hints to avoid mistakes. Even powers of 10 are, you can just take the square root in your head. And you'll notice here that it's exactly the opposite of what I did to get this number. I took 10 to the minus 4 times 10 to the minus 4. That's 10 to the minus 4 squared. It's 10 to the minus 8. If I take the square root of 10 to the minus 8, I'm going to get 10 to the minus 4. So I can pull that out of the square root. Okay, I can pull that out. That's going to be 10 to the minus 4 times the square root of 1245.86. Which is a lot easier to put into a calculator. Just don't multiply the 10 to the minus 4. If you wind up with an odd square root, like a 10 to the minus 5 or something like that, let's say you had, I'm going to make up a number, 5 times 10 to the minus 5. That's a really hard number to take a square root of. You could try and plug it into a calculator, but you can't do the 10 to the minus 5 in your head, is what I'm saying. So here's a tip. If you make that, if I move the decimal in that 5 and put it 1 to the left, okay, that would be a 0.5 times 10 to the minus 4. I could take the square root of that because that's an even number. Okay, because the square root of 10 to the minus 4 is just going to be 10 to the minus 2 times, and then I can take the square root of 0.5 in my calculator. The calculator can do that just fine. So the two methods I would recommend for this, if you don't put powers of 10 in your calculator, get yourself to an even power of 10 first and take that square root in your head. If you can put powers of 10 in your calculator, go ahead and put them in. Your calculator can do odd powers of 10 as a square root, no problem. Hopefully. All right. Anyway, so this bit here is just an example that doesn't apply to a problem it's not the numbers from the problem we're doing. We're still here. So 10 to the minus 4 times the square root of 1245.86. I'm going to do the 1245.86 in my calculator square root right now. And I get 35.29. I'm going to do 35.3. 35.3 times 10 to the minus 4, which is almost the end here. I just have to make it scientific notation, which is 3.53 times 10 to the minus 3. Okay, that is the concentration of my HI, so this should be in moles per liter. All right. And sure enough, that's about 10 times more concentrated than my other guys, my 4.79 times 10 to the minus 4. So I did get a bigger number than my H2 and my I2. Okay? So we always start, just to recap, we always start with our Ki expression. We plug in the numbers given to us in the problem. We're going to algebra that up and get an answer at the end. And put that answer in scientific notation. Okay, hope this is helpful. Go ahead and work through the rest of the problems. Check your answers on these, see if they were right. And then you can go on to the second half.